hypersonic, inflatable, aerodynamic decelerators have the ability to make the complicated and challenging tasks of entry, descent, and landing smoother and more manageable than ever before, all while giving us access to planets and moons we've only ever dreamed of exploring. Find out how next on Real World. Entry, descent, and landing technologies ensure precise and safe landings for NASA spacecraft. Each EDL is unique because of the atmosphere and the type and/or size of spacecraft being landed. But any spacecraft that flies through an atmosphere to land on the surface below encounters some common problems. With a HIAD vehicle, the difficulty of both entry into an atmosphere and descent through it are tackled with the same solution.
HIAD stands for Hypersonic, Inflatable, Aerodynamic, Decelerator. When I say hypersonic, that's because that's when you're going really fast. So supersonic you've probably heard of. Hypersonic, you're actually going more than 5 times the speed of sound, and often 10 or 20 times the speed of sound.
Then of course, you've got to slow down the spacecraft as it descends to the planetary surface. That's why researchers at NASA are rethinking the way we enter, descend, and land at Mars.
A HIAD is an inflated heat shield that by design is looking to replace rigid heat shields. A heat shield is what safely decelerates and protects your payload.
We have actually 2 distinct assemblies with the inflatable structure, and that gives the aeroshell form. It gives us the drag area and survives the pressure load or the aerodynamic forces that are being applied. Now the inner ply, the inflatable structure, it is incredibly strong. It's a Kevlar braid, but that can't survive the heat of re-entry, so we have to protect it with something, so we have a thermal protection system.
The intense heat experienced when moving through an atmosphere means that the spacecraft needs some kind of thermal protection system, whether that's the ceramic tiles on the shuttle or the blunt body heat shield on capsules from Mercury to Apollo and on the Mars Science Laboratory.
When we launch a mission to Mars or another planet, we have to put that aeroshell, that drag device, inside a launch shroud. And we're limited by that size. So whatever size rocket we're on, that's as big as we can make the aeroshell. The idea is to deploy something bigger.
Check out this physical map of Mars. Colors are used to show the relief, or the differences in land elevation. See those red X's? That's where we've previously landed spacecraft on the red planet. Notice anything about where they landed? They're all in blue and green areas, which are below what was the Martian sea level. You see, Mars has a really thin atmosphere compared to Earth's, so there's not enough drag force to slow a spacecraft sufficiently. So right now we're not able to land in all of this area in black because we can't get the spacecraft to a slow enough speed to land safely. But there's a lot of scientific interest in these areas. For example, there's evidence of geologically recent surface water activity in this area, which makes it particularly interesting to NASA geologists and astrobiologists alike. So we want to be able to study this region, but how?
So going into the Martian atmosphere is particularly difficult because it's a thin atmosphere. It's what I call a poor excuse for an atmosphere. So you're trying to go from a very high velocity, 5.5 to 7.5 kilometers a second, and get down to where you can survive the landing. Right now, though, with MSL landing that metric ton at below what was sea level at Mars, we're basically at the limit. If we wanted to go take that same rover to higher altitude where we've seen evidence of fairly recent surface water activity, if we wanted to take that rover to those altitudes, we can't do it with current technology. A HIAD, though, we can go larger. And with that same mass, larger aeroshell, we decelerate at higher altitudes and we can get to those higher altitude locations.
But Mars isn't the only destination with a challenging atmosphere and landing conditions. There are planets and moons throughout our solar system that scientists would love to be able to access. And HIAD technologies could make that possible.
I see HIADs as being a good door opener for NASA for future exploration of planetary bodies to help us bring those more advanced robotic rovers and explorers, and also enabling human exploration of planets in our solar system. One potential application for HIAD is to use them with the International Space Station to bring cargo back to Earth. Right now, cargo such as equipment, older equipment, or any equipment that we'd like to get our hands back on, it's difficult for us to bring back because of the size. And HIADs will enable that mass and those devices to be safely brought back to Earth.
And one of the other areas is access to space. We're always talking about low-cost access to space. You know, that's been the driver since the 70s, is how do we get more stuff to space at a cheaper price? Launch vehicle asset recovery is another area we would like to look at. If you could bring back the solar panels, the computers, the tanks, all these things, and reuse them, because most of these things can be used multiple times. And so a HIAD could be part of that solution.
HIAD saves space, mass, and money, making this innovative technology even more appealing. Remember that map of Mars? With the HIAD system, all the area that was previously off limits could now be within reach. Entry, descent, and landing. For those destinations with atmospheres, getting a spacecraft through the atmosphere so it can actually land on the planet's surface dictates much of the engineering that goes into the mission. That's NASA taking us to new heights. See you next time on Real World.